Well, my name is Rob Reynolds. Welcome to Calculus section 6.10. Today we're going to be looking at hyperbolic functions, and everything that we've kind of dealt with today, everything that we've dealt with for chapters 1 through 6 can kind of be applied to today's lesson, but just in terms of hyperbolic functions. For example, we've learned how to take the power rule. We've learned how to do the derivative of e to the anything is e to the anything. This is that du that I kind of make fun of. We've done a lot of trig, which hyperbolic functions deal a lot with trig, which you'll see here in just a second. But the derivative of the cosine of, this is the chain rule of a cow, is the negative sine cow, and then this is the decal. The derivative, so it's the derivative of the outside, write down the inside times the derivative of the inside. That's chain rule. So we've looked at all of these different rules, and we're going to apply those rules in a little bit different way. This looks like a parabola right here, but actually it's not a parabola. It's actually a hyperbolic function, which we're going to explore. Another case that you've seen the hyperbolic function is in the Gateway Arch in Missouri. So what the hyperbolic function is really just a point on this hyperbolic. So instead of it being a point on the unit circle like cosine and sine, we've got, or just like cosine and sine are points on the unit circle, we have points on this hyperbolic function. Instead of x comma y, we've got the x distance as cosh, and then the y distance as sinh, meaning hyperbolic cosine and hyperbolic sine. Here's some formulas which you will not have to have memorized. I'll provide a formula sheet for you, but here's the actual definition of hyperbolic cosine, and here's the actual definition of hyperbolic sine. And of course, there's tangent and hyperbolic cotangent, hyperbolic tangent, sometimes called tanh. I don't know if anybody says anything other than hyperbolic secant, but it's kind of fun to come up with sech and cosh. I don't know how to pronounce all this stuff, but here's some graphs of what that looks like, and we'll explore them a little bit more. If I were to take all those points and actually plot them, kind of looks like a parabola again, but it's not. But it kind of forms this parabola. The hyperbolic cosine kind of forms this yellow parabolic shape. And then the hyperbolic sinh kind of looks like an x cubed. So it kind of looks like an x squared. It's not. This kind of looks like an x cubed. It's not. But it's kind of just the general shape that they take on. But we're going to be focusing on these definitions and how we can apply them. You can see we already know that cosine squared theta plus sine squared theta in trig is equal to 1. Well, that's a plus, kind of like an ellipse has a plus sign in between, is set equal to 1. Now hyperbolic functions are set equal to 1, but we changed that plus to a minus. So again, here's the quick little proof of using these definitions of why hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. So here are some, again, trig formulas that you should recall. I sometimes call these the 1 plus 1 is second base, and then this 1 plus this 1 is 2 c's, or cosecant squared. So they say prove now, given that the yellow, prove this green. So let's see if we can work through this together. So just like in trig, we know that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. If I divide both or every term by cosine squared, hyperbolic cosine squared, I'll get 1 minus, and then hyperbolic sine divided by hyperbolic cosine, I'm abbreviating these things because I don't want to write all that out, it's hyperbolic tangent, and then 1 over hyperbolic cosine is, sure enough, exactly what you think it should be, hyperbolic secant. So there's part A. Part B, I see we've got a double angle here. So we'll work on that. Remembering we know that the sine of a double angle, that identity was 2 sine x cosine x, and they're saying, hey, show through these definitions that it's also true for hyperbolic. So let's see if we can use this. I'm going to do a quick let u, just do a u sub here. So if we let u be 2x, then I'll have e to the 2x minus e to the negative 2x all over 2 for my hyperbolic sine, because hyperbolic sine is e to the x, but I'm doing kind of a u sub. Every time you see an x, you can see I'm substituting that u sub, I'm letting it be a 2x. Well, this is the difference of two squares, just like x squared minus 9 factors to x plus 3x minus 3. This will factor to e to the x plus and minus, and then same thing but with a minus, because when you multiply e to the x times e to the x, you rewrite the base and add the exponent and get 2x. Well, if I separate this wisely, I'll get e to the x plus e to the negative x over 2 times e to the x minus e to the negative x. So I've just kind of separated this part out right here, and then if you want, I could say divided by 1, and that's true. I'm just decomposing that fraction. Well, this pink thing, if you recognize, that is the definition of hyperbolic sine, and then this is twice, if I double, hyperbolic cosine. So again, you could go back to this equation over here and just multiply everything through by 2 and see that that's true. So I'm writing that definition right there. So this equals 2 hyperbolic sine, hyperbolic cosine, and that's a pretty good algebraic proof. Here's how the author derives it. You can pause the video, and of course, hopefully you've downloaded the PDF file and you can look at and work these examples along with me. So again, you don't have to have these memorized, but here's a hyperbolic trig identities. And then here's just some regular basic trig identities, just so you can kind of compare. Some of them are exactly what you think that they would be, but every once in a while there's a surprise or two in here, meaning that the function doesn't quite work the way that you think it would work. I'll highlight those in here in just a second. So we've looked at hyperbolic cosine and hyperbolic sine functions. I wonder what the other 4 hyperbolic trig functions look like. You won't need to know this, but I thought maybe it might be interesting to look at it. So here's hyperbolic tang and hyperbolic secant. Of course, the other 2, hyperbolic cotangent and hyperbolic cosecant. So here's some derivative formulas. Again, I'm just going to provide a cheat sheet for you. We already know that the derivative of cosine is negative sine, so this is kind of interesting. This is not the way that you think it would be, because this actually turns out to be positive when you talk about hyperbolic. So don't get those definitions mixed up. So that doesn't behave the way that you think that it would behave. So the first example here, part A, we're going to do a u sub again. We're going to let u equal 3x. So I'm really thinking, what's the derivative of hyperbolic secant? And I'm going to come back here and say, aha, it's right here. And I just write the answer. I think there's a negative, yep, a negative floating around. And so I'll grab it, negative hyperbolic secant u, tangent hyperbolic u, and then I have to remember du, because I did a u sub. So the final answer, well, the du, the derivative of 3u, is just a 3. I'll pull that out front. So it's going to be 3 hyperbolic 3x hyperbolic tang 3x, and then the du I threw out front. Part B, it's the second derivative, so it's the derivative of the derivative. So I'm going to have to do the product rule, and again, chain rule. So again, if I do a u sub and let u be 3x, then the derivative of 3x is 3, and that 3 times this 3 is going to be a 9, and that's still going to be negative again, so negative times negative is positive 9. Secant 3x hyperbolic hyperbolic tanh 3x. That's the derivative of the first. Write down the second plus the derivative of the second. Oh my goodness. Well, the derivative of tanh, so I'm doing the product rule here. The derivative of tanh, well, again, a u sub, so I'm going to do negative 3 for the u sub. The derivative of hyperbolic tanh is secant squared 3x, and then write down the first. So I got another hyperbolic. And so, like combining some like terms, I've got hyperbolic tanh squared minus, let's see, negative 3 times this 3, negative 9, and I think I'm going to go hyperbolic cubed here. So I could actually factor out a 9 hyperbolic secant 3x, leaving me with hyperbolic tangent if I factor correctly. Always wonder if there's another identity in here, just because I know that 1 plus, not hyperbolic, but 1 plus tangent squared is equal to secant squared. So I wonder if, so then I know that secant squared minus tangent squared, not hyperbolic, is equal to 1. So I'm wondering if this is just the opposite, if this would be negative 1. I'm not sure. I think we'll check with the author. I might be able to play around with that, but I might just want to quit there. I'm going to go to part C, and we'll come back to part B and see if the author simplified that, but that might be a negative 1. I'll have to check on that. For C, I'm going to do another u sub. I'm going to let u be this square root of x. So du would be 1 over 2 square roots of x. Dx, and then if I multiply both sides by 2 and pop out that 2, I think I can replace that with 2 du's. So let's do a u sub here. I've got a 2 that pops out, the integral of cosecant hyperbolic u and then du. Everything up top just stayed. Remember, that's my u sub, and then my du, I think, dropped out. So I think that's right. So then this, I'm going to go to my cheat sheet and find out that it's actually negative hyperbolic cotangent of u, and then the u sub that we plugged in there was the square root of x. And then part D, I'm going to do another u sub. How about it be the inside function hyperbolic sine, because then du would be hyperbolic cosine, which I kind of like. So all of this is going to go du, and then I can rewrite this as the integral of just u cubed du, which is 1/4 u to the 4th. But my parameters are going to change. So I'm going to take this 0 and this ln of 3 and kind of I'm going to plug them in here. So hyperbolic sine of 0 I need to evaluate, and that actually 0. But the hyperbolic sine of the ln of 3, I may want to do through the definition. You could have done the same thing with the 0. But e to the ln of 3 minus e to the negative ln of 3 all over 2 is 3 minus. So this negative comes up here and makes it e to the ln of 1/3, because 3 to the negative first is 1/3, which is 1/3 divided by 2, and that turns out to be 4/3. So you're going to evaluate this between 0 and 4/3 and do the fundamental theorem of calculus. So I'll just throw here, so keep that 1/4, it's a constant, so just pop it out. So it's really 4/3 to the 4th minus 0 to the 4th, and then the final answer is going to be 64/81. So that one was a little bit rough because I needed to kind of evaluate this, but it's easy if I just go back to the definition of hyperbolic sine. So I still had a question about that part B. Yeah, right here. I don't know. I'm going to have to go to Wolfram Alpha and kind of play around with this. Evidently, that can't be simplified because I think the author would have done that, but I don't know. I'll play around with that some more. And let's see if we got, yeah, this one looks good. So then we're going to talk about some integrations of hyperbolics. Example 3, we're going to do some more u subs, then du is 2x dx. So if I take half, divide through by 2, I can replace x and dx. So there's my x, there's my dx. That gets replaced with 1/2, which is a constant, which I'll pop out. Hyperbolic cotangent u du, which is the natural log according to this definition. The absolute value of sinh u plus c, and of course the u was the x squared. Final answer. Author agrees. Next, we're talking about inverses. We're kind of going through the entire year of calculus. We're relearning everything, but instead of using trig functions, we're using hyperbolic trig functions. So again, you don't have to have these memorized, but you will need to know how to read these off of the cheat sheet to apply them. So in this one, we want to know, when does y sub 1 intersect y sub 2? And all we have to do is set y sub 1's function equal to y sub 2 and try to solve. Well, to solve this for x, we're going to do the inverse of both sides. So we're going to take the hyperbolic inverse of the left, and we'll take the hyperbolic inverse of the right. And then this side, well, you're just undoing, it's kind of like adding 5 and subtracting 5. Everything drops out, and you're just left with x. And this guy is the answer that could probably be simplified. So I don't have these memorized, but I see that that guy can be written right here. So I'm going to try that. Apply, every time I see an x, I'm just going to plug in that 5/3. So this becomes the natural log of that 5/3. Whoops, there goes my pen. 5/3 plus the square root of 5/3 squared minus 1. Reading off of this guy. So there's the 5/3 square root of 5/3 minus 1. And then I wonder if I can clean this up just a little bit. Since my calculator has a, I don't know, does your calculator, I'll have to play around with that too. A lot I have to play around with. I wonder if there's a button. Yeah, let me look for that. But let's do it algebraically and see if I can finish this up a little bit. So this is the natural log of 5/3 plus the square root of 16/9. Isn't that nice? Which is the natural log of 5/3 plus 4/3, which is just the natural log of 3. Now with the calculator a little bit, I can't find it other than under second catalog, and you can use your alpha keys to get down to the C, but there is a hyperbolic cosine function, and we wanted to know the 5/3, so there we'll give you the decimal equivalence, which remember we said the answer was the exact answer of the ln of 3. I'm hoping this is the same, and it is. So again, I found it in our catalog. Maybe there's a shorter way. If you find out the shorter way, can you shoot me an email? But your calculator does evaluate hyperbolic cosines. So then we take derivatives of the hyperbolic functions. We can take derivatives, go back, or integrals, and go backwards. So example 5, we do a quick let u equal 3x, then du is 3dx. And so when I take the derivative, I have to remember the chain rule and end up with a 3. So this says find the derivative. So it's 1 over 1 minus u squared du. And I just found out who du was. So 1 over 1 minus that 3x squared times the 3 gives me 3 over 1 minus 9x squared. And then for the second guy, I'm going to have to do the chain rule because I see a product here. So it's the derivative of the first, write down the second. Ooh, I don't want to do this problem. Oh my goodness. Plus the derivative of the first, write down the second, plus the derivative of the second. So the derivative of hyperbolic is 1 over the square root of x squared plus 1. And then write down the first. I don't know. You probably, I mean, at best, I see they have an x. You could pull out an x. I don't know. You could find a common denominator. I don't know what kind of final form you want this in, but if the answer is multiple choice, then it's leading you to, can you show me the algebra to get to this final answer? But I don't know, maybe answer A is the more simplified, but maybe answer B. I hope you can get there by finding a common denominator and factoring out an x. Oh, the author did that too. So practice adding fractions. The last example that I'll do with you, because the video is getting a little bit long, is finding the area underneath the curve. Well, of course, that means integrate. So I'm going to integrate between 0 and 3 of 1 over, and that looks to me like this hyperbolic inverse. And it looks to me like a is 4 because this is the square root of x squared minus a squared. So if I let a be 4, this is x over 4, because I remember that the integral of 1 over the square root of a squared minus x squared on a cheat sheet was that sine inverse of x over a, and that's true for hyperbolics as well. And so I want to evaluate that between 0 and 3, so the hyperbolic inverse of 3/4, which I've just found out that I can evaluate now on my calculator. I know this is a 0, so I could punch this and end up with 0.693 approximately. I'll leave part B for you, but part B is comes up with a pretty interesting answer at the end. Especially if you don't just pick up your calculator and type it in and just move from that. I mean, I should have shown you, if you wanted to find this exact answer, we could use that definition again. That's the ln of the x term plus the square root of that x term squared plus 1, which is the 3/4 plus the square root of 25/16, which is the ln of 3/4 plus 5/4, which is the natural log of 2. So you could punch in and see if that really is the natural log of 2. And then something similar like that should happen here. I mean, if you pick up your calculator and just punch it in, I'm not sure. If the final answer looks like this, then they want you to do this red step, kind of show me that you can work through there and actually end up with the exact answer, opposed to a decimal equivalence. So that's why I'm giving you multiple choice, because multiple choice will kind of lead you to the type of work that I'm looking for. And if I'm looking for this as an answer, then I'm not really interested in you picking up your calculator and just finding out the decimal equivalence, and then saying, oh, well, this decimal matches that, so this must be the answer. Well, that's not the purpose of the multiple choice. The multiple choice is saying, hey, show me the work to get to this step, and you might have to go through a definition to do that. And so that's what I'm testing over, to see if you can demonstrate your content knowledge through that definition. So make sure you don't just jump to an answer, because I'm not interested in your answers. I'm more interested in your work. If you have any questions, feel free to email me. Thanks.